Hello and welcome everyone to our webinar. We are really excited to know about the developments in control engineering and artificial intelligence are opening the way to a wide range of exciting robotic applications of great benefits to our society. A robot, however, typically relies on a large amount of software that determines in behavior, which affects and is affected by its environment. Today, in this webinar, we're going to present an approach to the design and verification of robotic software that takes into account the assumptions that can be made about that environment. And Professor Anne will explain such approach and demonstrate the use of two tools for capturing assumptions and providing properties of interest. So today we're going to have Professor Anna Cavalcanti and James Baxter and Gustavo Carvalho. Let me first introduce Professor Anne. Professor Anne, she's a professor in computer science at University of York, and she's the leader of the RoboStar Center of Excellence on Software Engineering for Robotics. And today she's going to actually talk with her team mainly about how can we define operational requirements in robotics. Professor Anne has many publications. She has a book about software engineering for robotics, and she has over 46 articles. 4 of them are public accessible, and she has over 4,000 citations, and her work is significant in the area of software engineering on robotics. Also, her team, they have experience. James Baxter is a researcher at University of York, and his experience or interests are in the area of software engineering, particularly formal methods for the past 4 years. And he has been working on robot test projects, developing a verified model-based testing strategy for robotic systems. The other member is Gustavo Carvalho. He's a lecturer actually at Centro de Informática of the Federation in de Barmalo in Brazil. His main interest also in software engineering with emphasis on tests and formal methods. He has 30 peer-reviewed publications. Also, he has papers for international conferences and journals, well-recognized journals, including journals in SOSISM and IEEE. And in 2021, he served as a chair of the formal methods special group at Brazilian Computer Society. So welcome, Professor Anne and your RoboStar team. It's your turn now. Thank you.
Thank you very much. Thank you very much, Dr. Abograd, for the generous introduction. Thanks also to the BCS team for the invitation. It's a real exciting opportunity for us to be able to address the information technology community And I also see around the audience some very well-known names on the formal methods community as well. It is a pleasure to be here this evening to be able to talk to you about the work. It's not my work, it's the work of the RoboStar team. As you mentioned, it's a center of excellence on software engineering for robotics. It did start in New York, but we now have branches in Norway, China, France, and in Brazil as well. This is here represented by Gustavo. And so it is a real pleasure that the three of us, James is a colleague in RoboStar York, Gustavo is the same RoboStar Brazil, present this part of our work, which is on software engineering for robotics. Software engineering for robotics is an area of emerging technology, but there are others that are interested. The book that Dr. Bugrad mentioned is actually an edited book of chapters from colleagues from all over Europe, putting their ideas on what should happen in software engineering for robotics. Our approach in RoboStar is, however, distinctive. Our approach is that, our vision is that we should complement existing techniques. The roboticists have their own practices that work well, but we can complement with more sophisticated approach to software engineering. We have developed a set of domain-specific languages, and this evening I'm going to talk to you about one of them, which is particularly concerned with the capturing of assumptions about the environment in which the robots are supposed to work. What are the operational requirements of these robots? And also another distinctive feature of our approach is that all these notations, they have a mathematics semantics. From all these notations, diagrammatics or based on controlled natural language, we can automatically generate mathematical models that then we can use to validate and verify the system using sophisticated modern approach to software engineering. And what is our motivation? We all know, I think I don't need to motivate this audience, the revolution in the area of robotics that we are all living, and all the promise that advance in control engineering and artificial intelligence have in the potential impact in our society. But for all these advanced approaches, their approach to software engineering is very outdated. So it's basically what we call code-centric. So at the moment, if we are lucky, roboticists draw a state machine-like diagram that indicates what the system should do. I don't call that a model in the engineering sense, because it's just a drawing that they use some drawing package and cannot be used for us to analyze in any way with a tool, for example. From that, they develop a simulation. That's the first artifact that they develop that is really precise, but it's code. It's code for a simulator. It depends on whatever libraries a particular simulator has to support the simulation of the hardware and of the environment. Once they are happy with the simulation, then they go to the deployment, the low-level code that actually runs on their robot. Normally, at that stage, they find discrepancy. They find what's called a reality gap between what they observed in the simulation and what they can observe in the real world. At that moment, the simulation goes out the window, the state machines have gone out of the window completely, and they start on a trial and error using the very outdated and costly approach where they change the code and try again and again and again. And with this, they cannot at the end guarantee anything about their system. The only guarantee is that they didn't find any error. But with the promise that we have with robotics, that it will come into our homes, that it will be having a role in assistive care and in healthcare, we cannot accept this situation. And also, it's very expensive. So the RoboStar approach is about changing this code-centric situation to have a model-centric situation, but where simulation still plays a big role. So as I said, we developed a variety of domain-specific languages that allow the roboticists, using either controlled English or diagrams in a way they are familiar with or reasonably familiar with, to move from this situation where the first point that in which they are precise is in the simulation. But tonight, what I'm presenting is the language that's called Robo World. I'll first give you a short motivation for the use of Robo World. I'll give you an example based on a firefighting UAV, and then I will give you more details about this notation. I'll present a meta model, an intermediate representation that's derived from the meta model that we use in developing our tools to generate those mathematical descriptions that I mentioned to you. The two demonstration will be given by my colleague Gustavo Carvalho. It's a tool whose development he is leading. Then I will tell you a bit more about the semantics, about that mathematical model that we have for these documents written in Robo World, and how these mathematical models can be used for verification. Again, we will have a demonstration of two tools that are used in verification, and that's going to be led by James Baxter. And finally, I will present some conclusions and future work. So why Robo World? Well, a robotic system, it doesn't exist in isolation or in a desktop or in a dedicated computer like an information system. It is what we call a cyber-physical system, and it affects and is affected by the environment in which it runs. So if I want to do any sort of verification, I need to understand what are these conditions in which the system is going to run. So if I have the example that I'll give you is a firefighting drone. That's behavior will be very different depending on the conditions of the weather, the rain, the speed. It will depend on the location where it is, how far it needs to go, which fires it's going to identify, and so on. So we need to document these operational requirements. And roboticists, they know that they need to do that, but normally they don't worry about that at the start. It's only at the very end that if you ask them this, but when I was designing it, I didn't mean for it to work in such conditions. So we are creating a language that is going to help, but it's still very usable with the use of controlled English, but with the control providing the possibility of us generating mathematical semantics and also guidance to the roboticists, so that they can write these operational requirements and use that information in a more effective way. So these documents in controlled English that document the operational requirements, they are complementing platform-independent models of the RoboStar framework, in particular of a language called RoboChart, and they have an important role in testing, simulation, and proof. Why is this? Because let's take, for example, test. If I am trying to define which tests am I going to put my robot through, they must be tests that are satisfying the operational requirements of my robot. Therefore, I need to know what these operational requirements are. And in a model-centric approach, which is the RoboStar approach, we can generate these tests automatically, but we need information. And that information will come from a Robo World document. The same applies to the simulation. If I want a simulation, I need to know what are the conditions that the scenarios that I'm going to use in my simulation are going to hold. And proof as well. If I want to prove properties, proof here being as opposed to testing. Test will consider few scenarios. Proof will give you an exhaustive account of the behavior of the system and give you guarantees, firm guarantees that the expected behaviors are valid. So we need to understand what are the assumptions that we can make when we're making this proof. Those assumptions, they are described in a Robo World document. So a Robo World document, it has a fixed structure, and this structure includes assumptions. These assumptions will be about the arena. The arena is the name that we use for the area where the robot is going to work. There will be assumptions about the robot. The robot may have some components that are essential for its behavior. And there may be other elements. We'll see an example. There may be a building, there may be fires, there may be particular regions called home. So there will be other elements, and we all need to know about them and about their properties, the relevant properties for the system. And there will be mappings as well. These mappings will solve the situation where we have a RoboChart in this case, but a platform independent model for the software. That's something that it's not about RoboStar. Every technique in software engineering wants to have platform independent models of the software. But how do those platform independent models connect to the assumptions that we're making about the environment? That's what these mappings are going to define. They are going to describe how the events, input and output events, operations and variables used in the software reflect and are reflected by the environment. So that's the motivation. Basically, in summary, testing simulation proof of a cyber-physical system like a robotic system, we need to know what are the operational requirements, okay? And we want them to be written in a way that's accessible to the roboticist. So we use controlled natural language. So my example, as I mentioned, is a firefighting UAV. It exists. My colleagues in Leeds, they have built it. It was inspired by a challenge for an international robotics competition. And there is a picture for you of the drone. It has a variety of sensors and actuators. And we have written a model for this firefighting UAV. We have the real RoboChart model. It has 21 robotic platform services. It's, these are the assumptions that the software model makes about the platform. There are 21 services that it requires. We have 2 controllers, 9 machines. We generate automatically the mathematical model for this example, thousands of lines of mathematics that we wouldn't want a roboticist to have to write. I don't want to write it, but we can obtain automatically as well. And all the artifacts, RoboStar approach is very comprehensive. It caters as well for the platform model. So the picture that you have here in this slide, this one here, is a picture that's automatically generated from a physical model of the robotic, what I call here a P model, that can be used to generate automatically an SDF document or a simulation as well, a simulation model, and all that used to add value to the practice that the roboticists already adopt. So I'm going to present you very briefly here. I don't need you to understand the details. A RoboChart model for a toy version of the firefighting UAV. So a RoboChart model is based on state machines. So it's a very, in one sense, very standard, and that is a positive side, but it's enriched because it allows you to deal with the time properties. Again, another feature of a cyber-physical system is that time is extremely important for the behavior of that system. So our notation is enriched in that way. But what we have here in this picture is the outer box is what we call a module. Its name is the Simple Firefighter. And this module is representing the control software for the robot. And a part of a module that's extremely important is the robotic platform. It's here called UAV. And that robotic platform in a RoboChart model, it is a description of services. We're not describing any particular platform. It could be the one that I showed you in a few slides ago. It could be another one. We just say, what are the assumptions about the robotic platform that we make? And here, in this very simple model, we identified 2 interfaces here, commands and embedded I, that describe what are the service of this platform. Embedded I gives me the name of 5 events that must be available in the robotic platform for the software to work. For example, I should know when a fire is detected. I should know when the fire is lost, when there is a critical situation, either the battery is low or there is no water and so on. There are also some operations like take off or go to building, there is a building, or search the fire, go home, and so on. So these are not descriptions of a particular platform, but descriptions of services that we require from the platform. In a module, and I don't need you to understand the details here in this example, besides the platform, that's here UAV, we also have a controller, here called planning, whose behavior is defined by a state machine, as I said. And here's the state machine, but I don't need you to understand the details of the state machine. I would just highlight here to you the fact that the state machine uses commands like take off, which are available in the robotic platform, or go home. It also uses events like fire detected, and these are all events that correspond to something in the environment. The name is suggestive, but what do these names mean? And it is the Robo World document that is going to make that connection between what the software is expecting or doing and what effect it would have in an environment, and in which kinds of environments it would be allowed to work. So as I said, a Robo World document has a particular structure. The first part of a Robo World document are the arena assumptions. So the arena, as I said, is the area where the robots expected to work. And here's an assumption that we're making. The arena is three-dimensional. It could be two dimensions. There are some simulations, for example, that are simplified. But for this application, the arena is three-dimensional. This is a precise document. It's English, but it's controlled English. It's a precise document that we can use a tool to analyze. The second assumption about the arena is that the width of the arena is 50 meters. We could say it's at least 50 meters, or it's greater than 50 meters. The depth of the arena is also defined there. Another aspect of an arena, every arena has a ground, and sometimes the gradient of the ground is relevant, very relevant. In this case, we're saying the gradient of the ground of the arena is 0. It's a flat arena. And the motivation for that is because I have a building. And now I can say a few more things specific, very specific to this application. The arena has one building. The height of the arena is at least the height of the building plus 1 meter. Why is that? Because I need my drone to be able to go fly over the building. So if I'm generating a simulation, which is one of the many things we can do using the RoboStar technology, I need to have that information. The arena has fires. The arena has a home region. The speed of the wind is less than 8 meters per second, and that it's not raining. I haven't made up these assumptions. They are real assumptions of the real application. It's not about the toy example I just given. So the arena assumptions are basically about the shape of the arena in a sense, but also about elements that can belong to the arena, entities and regions that can belong to the arena. Here we have a building, we have as an entity, for example, we have a home region. Then I can write assumptions about the robot. Robot assumptions. My assumption here is very simple. The robot is a point mass. I could actually, and RoboStar technology has support for that, go all the way from it's a point mass, it's a simplification that I'm making that's very common to be made in simulation, all the way to here's a particular physical model of this robot where I identify every what's called link or joint sensors and actuators of the robot. We have a diagrammatic notation to specify that. And that diagrammatic notation can be, is part of Robo World as well. We could say, and here's what it looks like. You saw what we were able to do about the little drone. That could be part of our assumptions if we wanted. But in this simple example for now, the robot is a point mass. But there are other interesting assumptions that we make. The initial location of the robot is at home, is at that region that we called home. The robot has a tank of water that may be either full or empty. So a little bit about the state of the robot, which is relevant for reasoning, maybe full or empty. The robot has a search pattern, which is a sequence of positions. Again, another information about the data that needs to be available in that robot, information that robot needs to have. And then there are element assumptions. We have arena and robot. Every application will have an arena and a robot. But when I define the arena, I may have defined other elements, and I can say some things about them. So for example, the building is a box. And the building has some constraints on its dimensionality as well. The building is at least 6 meters high and up to 20 meters high, is at least 10 meters wide, and so on. A fire can be on the floor. That's something the colleagues from the competition that I mentioned that motivated the application gave to us. The fire can be on the building between 5 meters and 18 meters high, again, coming from the competition. Then there are a few things that may look strange, but it isn't, because they are about simulation. In the environment where these robots were being tried when we had the competition, fires were simulated by a hot plate. And so I was able to say that a fire is 36 millimeters wide, 6 millimeters high, and it's not very deep. The depth is irrelevant, because that's the simulation environment in which I'm interested. And something about the region, the home is on the ground. So all this are assumptions about the environment that we can make, okay? And now I had my RoboChart model, which was platform independent and had some events and operations that it requires for that control software to run. I have some operational requirements described in English. How do I make these things match? How do I combine this software model and this model of the robot, not a model, and these assumptions about the robot and the environment? This is done by mappings, and we have 4 categories of mappings, and I'm going to illustrate some. So the mapping of input events. For each event, I can say how that event is a factor of input event, how it is coming from the environment to generate that event. So here, we have a first sentence that says, the event fire detected, one of the ones in the model RoboChart, occurs when the distance from the robot to the fire is less than or equal to 0.5 meter. So I'm talking about properties of the environment, and those properties, they are telling me when that event happens, when the software will be told that there is a fire. That's an example. There will be others going ahead. Another one about an output event. One of the output events is a spray. One of the functionalities of this robot is to spray some water to quench the fire, of course. So we say when the event spray occurs, now it's the software saying, I raised an event, I raised an output spray. Well, if the robot has a tank of water that is full, we mentioned that robots have had tanks of water that could be empty or full. A fire that is in front of the robot and less than 3 meters away disappears after an amount of time between 1 minute and 3 minutes. So our language has time, as I mentioned before, and the tank of water becomes empty after 3 minutes. So this is a description of how the behavior of the control software will affect the environment that we have. We can also map the operations. So here's an example. I'll give you 2 examples here. When the operation takeoff is called, so we had such a command in such an operation in the command interface. When the operation takeoff is called, the velocity of the robot is set to 1 meters per second upward. So that is the effect of calling that operation on the environment, it's movement of the robot. I can be very precise. I could say the operation search fire is defined by a diagram. So if I have a very complex operation, I can specify it using a state machine. Here it's just sketched. And I just wanted again to tell you why this example. Robo World is a unified language. It's part of this unified approach to the developing robotics applications. And that's why it allows you to define diagrams as well as English. So this is my example. If anybody has any questions, please feel free to put them in the chat and I will address them. But going on for now, I'll just use the meta model of the language to give you an overview of what's going on. So the meta model defines the types of assumptions and mappings that can be described. I've given an example, but the meta model will makes that precise. The meta model is realized by a concrete grammar that's going to be exemplified by Gustavo. And that basically that concrete grammar will relate the meta model with actual English sentences. And Gustavo is going to tell you a bit more about the framework that he's using to deal with these English sentences, which is the grammatical framework, which is absolutely excellent. It is helping Gustavo demonstrate to deal with word inflections, agreement, and so on. And so we have these two levels. What's the structure of my language? What's the concrete grammar that we can use to write sentences like I just described for you? So the meta model is simple. I don't expect you to read this slide at all. I just wanted to show you it's so simple, it fits in one slide. But here is a bit more about it. So a Robo World document, it has 7 components. The first component is the arena assumptions. We have 0 or more arena assumptions, and they are defined by a statement. It has 0 more robot assumptions, and the robot assumptions is either a robot statement given by an English statement or by a physical model, as I mentioned. An element assumption we can have 0 more element assumptions, and they are each given by a statement. Then we have the mappings. We have an input mapping, an output mapping, an operation mapping, and a variable mapping. I didn't illustrate that. But let's look at input mapping. The input mapping has a name, which is the name of the input event that we are dealing with, and that has one conditional input. That conditional input can be of several forms. It can be an input sometimes, input always, input never, or input anytime. And I'm going to give you some examples of this conditional input. So I can say the event of obstacle occurs when the distance from the robot to an obstacle is less than a meter. That is a conditional input, input sometimes. When that particular condition holds, then the event occurs. The event angular speed is always available. That means that the robot can always read the value of a value from that event. And which value is it? I have an associated sentence, and that communicates the angular velocity of the robot. So I'm here indicating in blue what are the keywords of Robo World. It reads very natural, but the event occurs, is always available, are keywords. Obstacle and angular speed are identifiers that we're using for our model. So these conditions, they are, as I said, this input sometimes, it has conditions. Conditions, they have a subjunction, and they have a collection of statements, 1 or more statements. And these statements can be of several forms, can be passive, can be active, modal, and so on. So here's an example of conditions. Conditions is, here's the subjunction, it's the when, and then you have 3 sentences. The distance from the robot to the source is less than 1 meter, comma, that's a keyword. The distance from the robot to the nest is more than 2 meters, and another keyword, and the robot is carrying an object. So this statement level is handled by the concrete grammar and grammatical framework. We also have item phrases. In fact, I should say the statements, they are statements about item phrases, and item phrases here on the right. Here it is, item phrases, they can be, they can have a pronoun, they can have a determiner, they can be a quantified, and they are talking about a particular item that can be basic or compound. So examples, pronoun, it, determiner, d, angular velocity, quantified one, 1 radians per second upward. So all these are terms of this particular language. And what is great about this language, it looks very natural, but it is very controlled, as the meta model that I presented just indicated. And that means that we can create, we can have the structure of the language to help practitioners, but we also have well-formedness conditions. Those well-formedness conditions will tell practitioners, oh, you made a mistake. And there are some basic things, but easy to forget. The ground is a region of the arena, so every arena has a ground. The gradient of the ground is a non-negative number, so you cannot say the gradient is false or -3. The determinant of the robot is always D, because the language, for now at least, is just for one particular robot. We're not dealing with collections yet. And then there are issues of compatibility of the RoboShard model. So the inputs and output events mapped in the Robo World document must be precisely those of the associated RoboShard module. So all these things are statements, are conditions that we can check once a document is written. That structure of the document, it's elaborate and very flexible. And we also have an intermediate representation. The intermediate representation, it is there to allow us to represent that meta model, grouping information in a way that will do two things. It will allow us, I have my Robo World document, I have its intermediate representation, that's a technical representation. It's not another document, it's a technical representation. It allows us from it to generate the mathematical models that we want, to generate the simulations that we want, to generate the tests that you want. It's a more convenient structure than the structure of the meta model, and I'll show you why in a minute. But it's also giving us some insulation. This language will grow. We have used a few examples, less than 10 examples, to define the structure of our language. It's very general. The grammatical framework allows us to be very general, but we expect that the language will evolve. And that intermediary representation will provide insulation from small changes to the language. Okay, so we can, for example, we can decide, we're going to be more flexible here. We allow directed and passive voice. It doesn't matter if we capture that it's exactly the same concept that is being reflected. We don't need to change the transformations that we do from the document to the artifacts of interest. So it is important for evolution, and also means that we can give that mathematical account using a variety of notations. So I'll briefly tell you about the intermediate representation. The intermediate representation for the mappings, it doesn't change. The mappings are already very constrained. But when it comes to the assumptions, then we have identified here some key components. So in the assumptions, we say, okay, every document talks about an arena. So in the intermediate representation, we have exactly one arena. The arena needs to have a dimension, needs to have a gradient, either explicitly described or as an assumption. It may have some regions. Regions have dimensions and may have other properties. It will have a name, for example. An arena, we will also have, an intermediate representation also have entities. We declare those elements when we specify the arena, but what we want to know is information about each of the entities. The building, what are the restrictions? The wind, what are the restrictions? So all these entities, they can be represented each individually. There can be 0 or more entities. And finally, we have the robot, right? So the robot, it has a body. The body can be just a description, a sentence in English, or a physical diagram model. An entity, it can have several components. We had an example, our example didn't have that, but we could have said that the building has doors, has windows, and we would be able to describe those components of the entities there. And then the entity also has a name, which is an item phrase. So the intermediate representation collects together all these concepts that are being introduced in the document in a way that makes it easier for us to capture the meaning. So I'm going to give you another example, which is the example that Gustavo is going to use in his presentation. This toy example is an example of a Ranger robot. So it's a very simple robot. You can imagine perhaps one of these vacuum cleaner robots that can move around. So the important point for us in this presentation is that we have here the module. It's called Ranger. The Ranger module has the robotic platform Ranger RP that provides here the description of the interfaces where we have we say that we can have a detection of an obstacle or an operation move. And what we're really interested is in the English. Arena assumptions. This arena is two-dimensional. The ground is zero. The gradient of the ground is zero. The arena has obstacles. The robot is a point mass. Element assumptions. 1/4 of the arena contain obstacles. That's an important thing for simulations normally. If I'm generating scenarios to test, how many obstacles am I going to put? 1/4 of the arena should be, in this example, 1/4 of the arena should be occupied with obstacles. The obstacles are as well at point masses. And then we have the mappings of the input events and of the operation. Very simple in this case. The event obstacle occurs when the distance from the robot to an obstacle is less than 0.5 meter. We saw that example before. And the other one, when the operation move, you see here move with two parameters, LV and AV. When it's called, the velocity of the robot is set to LV meters per second and blah, 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 blah. Okay, so that is a little example. And Gustavo is going to show to you this example and also a bit about the firefighter as well. So Gustavo, please, I am going to stop sharing my screen now. And if you could go ahead and share your screen and make a demonstration. Is that all right?
Yes. I think that we had a question in the chat. Do you want to address it before I proceed?
Okay.
Or should I?
Worried about when tank is not 100% full. I'm not quite sure I understand the question. I'm not sure what you're worried about.
You can do the second question.
And the second question, can you model variable qualities such as reliability? Not at the moment, no. And again, I would be very curious to understand what the concern is and what the feedback is there. It is not what we're presenting today is not about the model variables. It's about the assumptions of the environment. And so I don't know if that's the issue. Perhaps we can chat at the end, Tom, if you could come and talk more. I would be curious to know what you're concerned about. Gustavo, please go ahead.
Okay, so let me share my screen just a second. Can you see my screen?
It's got a black box. It's gone now. It's okay.
Okay.
Yes, yes.
So it's working properly now. Okay. So first, I would like to thank the organizers for the invitation. And in my talk, I'm going to demonstrate the Robo World editor. So the Robo World editor is part of Robo2, and Robo2 is an Eclipse-based application. As it has been said before, it's the result of collective effort. And I would like to particularly mention my master student, Francisco, who has been actively working on the Robo World editor. So here I have the project for the Ranger example, and I have a file here with this extension, the .env file. And the Robo World editor is automatically associated to these kind of files. When you open the editor, you're going to see two pages. So you have a page for the dictionary, and you have another one for the Robo World document. In the dictionary page, you are able to add words that are specific to this example. So in this case, to the Ranger. It's important to say that in the Robo World language, we have a lexicon that is composed of words that are common to the robotic domain. So in the dictionary, you should only add words that are specific to the example you are dealing with. When you manipulate the dictionary, so when you add new words, for instance, you need to provide the tool with the inflection forms of that word, if applicable. So for instance, when you create a noun, you should specify the singular and the plural forms of that noun. And this information is very important because the grammatical framework, which is used by this tool, relies on this information to check agreement between parts of the sentence. In the Robo World document, the user has the option to see the whole document as a raw format, as a raw file, so with just plain text. But I would say that in general, the user, at least the least experienced user, would use the graphical user interface to edit the document. Here you can select the kind of sentence you want to add or edit or remove. So you have arena assumptions, assumptions about the robot, assumptions about all elements that are in the arena, and also sentences regarding the mappings. To illustrate some features that are provided by the grammatical framework, I'm going to edit the sentence that says that obstacles are point masses. So if instead of writing the sentence as it is, I write the obstacles is point masses. As you can see, the tool raises an error because the token is not expected in this context. And this information is given to us by the resource grammar library, which is part of the grammatical framework. So this tool is capable of detecting that obstacles are in the plural form. So the tool checks agreement between different elements of the sentence according to this information. Another interesting feature here is that besides checking syntactical aspects, we are also capable of checking well-formed conditions, as mentioned before. So here I have the sentence saying that the gradient of the ground is 0. If I write instead the gradient of the ground is 3-dimensional, you're going to see that an arrow is raised here, but actually this is not a passing error. So from the perspective of the underlying controlled natural language, the sentence is fine, but in terms of the semantics, it doesn't make sense saying that the gradient of the ground is 3-dimensional. So this is a kind of support that the Robo World editor gives to the user. To illustrate how to use the tool when you are creating a project from scratch, I will now consider the firefighter example. So you can come here, create a new project, which is going to be a RoboStar project. I will give here a name, so firefighter demo. And now I'm going to create a blank fighter env file. So you can see that the dictionary is empty. Also, the Robo World document is empty. Since the Robo World language has a lexicon, as I said before, you can start writing some sentences from scratch. One interesting feature of the Robo World editor is that it guides you on using this underlying controlled natural language, the grammar. So when you say that you want to write a new arena assumption, you can click on help, and the tool will dynamically traverse the grammar and see what are the options for creating this kind of sentence. In this situation, an arena assumption is created after a statement. But then you can ask the tool, okay, but how can I create a statement? And now the low-level details start to appear. So this controlled natural language allows you to create statements in different forms. In this situation, where I want to write that the arena is 3-dimensional, I should select the second option, where I'm writing a sentence in the active voice using the verb to be and an adjective. So now if you select, okay, what would be an adjective? The tool lists the adjectives it knows so far. So in this case, 3-dimensional. And what is an item phrase? Well, an item phrase can be created using, for instance, a determiner in an item, as we have explained before when covering the meta model. So the determiner in this case would be the, and the item would be a basic item, where the basic item would be created from a noun, and the noun in this case would be the arena. And you can see that now the sentence is full parsed, and you can add this sentence to the Robo World document. If you are a more experienced user, you may rely on the help on sometimes, but you can just start writing the sentences with no help. So regarding an input event mapping, I know that the sentence has some keywords, so you should say that some event occurs when some conditions hold. And I can here say that the event fire loss occurs when the distance from the robot to a fire is greater than 0.5 meters. Note that now the tool is complaining about the token fire, because fire is a word that is specific to this example. It's not part of the Robo World lexicon. So you can come to the dictionary and say, okay, I want to add to the dictionary a new noun, and this noun is fire. The plural form is fires. And if I go back to the Robo World document, and now I try to write this sentence, you can see that now it's accepted by the tool. It's also important to say that besides checking for syntactic and semantic aspects of the language, this tool is also capable of generating automatically precise semantics for this document. At this moment, we can generate a discretized semantics using the process algebra CSP, but we are extending the generator to consider a continuous semantics based on sci-fi circles, as we are going to explain next. And to conclude my demonstration, I would like to briefly show you some files that are manipulated in background by the tool. So when you create a new project and you have a dictionary for that project, a file is created with the words that have been added to that specific dictionary. And in the concrete version of this file, that's the place where I'm explicitly relying on definitions of the grammatical framework. So here I'm using functions from the resource grammar library to create nouns, verbs, adjectives, adverbs, prepositions, and in terms from all the categories. It's also interesting to note that the ranger is extending the Robo World language. And the Robo World language is the place where we define the notions from the meta model using the GF. So here we have the notion of a basic item, of an item phrase, and also statements, conditions, all of that concepts that are in the meta model. And I have functions describing the different ways of creating elements of these categories. In the concrete realization of this grammar, I use the concepts of the GF to enforce agreements. So here I'm using functions like creating a common noun from a noun in a noun phrase. That's the place where I create verb phrases, adverbs, and other elements. And in the end, I also have the lexicon of the Robo World, where we have placed, as I said before, some words that are common to the robotic domain, and that we believe that can be reused across different projects. So that was my demonstration of the Robo World editor. So I think that now I will stop sharing my screen so that we can proceed with the presentation. Thank you.
Thank you, Gustavo. Thank you very much. I will go back to sharing my screen, and I will now talk about this semantics. I know that most of the audience is not working in the area of formal methods, which is this area that gives mathematical meaning to the notations that we use, and explore this mathematical meaning to add value to design and verification of systems. But I must say something, because that's a distinctive feature of our work. The RoboStar framework is very modular. For example, we don't need to, Robo World document does not need to be associated with a RoboChart model. It could be associated with another model, control software model, written in another language, as long as it identifies those services, input, output, and input and output events and operations, then that will be compatible with the Robo World document. In the same way, we could use RoboChart with another language, but the important thing is that we need to have that unified mathematical semantics at the background, so that we can then use approaches to consider, in combination of the specification of the software and the assumptions about the environment, to add value, to generate tests, to generate simulations, to carry out proof, which as will be demonstrated in a minute. So this is really distinctive and really important. I will give you at least a flavor of what goes on. So all the RoboStar notations, they have this semantics, this mathematical version that is automatically generated for all of them, written in a process algebra for refinement called CSP, Gustavo already mentioned, and also with a basis in the work of Tony Hall and Regi Fang called UTP. In the case of Robo World, what we have special, we can't use just CSP. Why not? Because we have the continuous nature of the arena and of the movement of the robot. So when we give a model to the software using state machines, like in UML, for example, that model is discrete. A digital model, a model of a digital artifact that is discrete. The model of movement, the model of light, the model of voltage and torques and so on, that's continuous. So our mathematical description needs to be hybrid. There are several options to give hybrid behavior, to describe hybrid behavior formally. We use one that's called Sci-Fi Circus, which builds on Z, builds on CSP and Z and another notation called Circus. The important thing for this audience to remember is that it's a hybrid model. And that brings a lot of challenges, and we have addressed some and have more in our hands, as I'll say at the end. So what is common to this class of notations called process algebras? Everything, systems and components, and these assumptions as well, they are described by processes. And you can think of a process as a black box that interacts with its context via events, where these events are atomic and instantaneous. And the different feature that we have with Sci-Fi Circus is that we can specify as well, via differential algebraic equations, the trajectories, the equations that define the behavior of sensors, actuators, of movement, and so on. So we have this notation, Sci-Fi Circus, that we are giving semantics to Robo World in. So I will just give you an idea of the structure of the semantics. First of all, we have the semantics for RoboChart. It's a semantics for a RoboChart module. It's a process. It's discrete. It's pure CSP. But it needs these services, doesn't it? So these services are represented in the model by events that are the output or input CSP events that need to be provided by the mathematical model of a Robo World document. So the Robo World document process, the process that represents that Robo World document, also has two parts. One capturing the assumptions, it's a process that captures the assumptions, another one capturing those mappings, the mappings of input and output events of operations and variables. So those mappings, they captured how the output events are realized and how the operations are realized. So inside the environment, we have one process that represents a component that's very important, which is the robot movement. So basically, intuitively, you can think the environment assumptions are basically telling you how the robot moves in its environment, in its arena, right? But that movement will have to be interrupted every now and then. When it's going to be interrupted? If there is a collision detection, for example. So the semantics gives account of that. There were obstacles, there was a building, there was a person, whatever, the robot collided. That needs to be said because that has an impact on how the effect of the system, how the behavior of the system will proceed from there. As the robot collided, it doesn't move anymore. What can happen next? It will need to be the software that's going to handle that. Another situation that can happen is that we have to get and set some variables. For example, if I have the operation move, we set in the mapping that it needs to set the velocity of the robot. So the mapping process will say, the operation move was called by the software. That's something that the module process will say here. Then that operation will say, I've been called. Then I need to interrupt the behavior of the robot movement, the evolution of that movement, to change the value of a variable. And that's setting those variables will be something that needs to interrupt it as well. And also, we will need to be interrupted when certain conditions hold. For example, if I get very close to an obstacle, that needs to be informed to the mapping, because then the mapping needs to say, okay, the conditions that characterize that input hold, therefore I need to go via the mapping and get to the RoboChart module and raise an event. So this is, in general terms, a kind of black box account of the behavior of a Robo World that is described by a Robo World document, a collection of behaviors that's described by a Robo World document. And the fact that we can have this account using this process algebra means that we can have that you can use tools for verification. We can use tools for test generation, where we say, okay, using those mathematical models, we can define which tests you generated from the software that are feasible. You may be generating a test that is for an environment that's not valid. Using that mathematical account, we can say, this environment here, or this test here, does not satisfy our assumptions. I have to discard it. A simulation, we can check a simulation and say, is that satisfying these assumptions? And one other thing that we can do is to prove properties. We can prove properties of a system, saying, taking a combination of the behavior of the environment and the behavior of the software. Using just the software model, we can say, when the obstacle event happens, then the operation move is called. Okay, that's the software. But how about in the environment? What happens? Well, we could say then something different. When the robot gets less than ½ meter from an obstacle, then after a certain amount of time, the robot will stop. This is not a software property anymore. It's something that relates something in the environment, that's the obstacle, with the something about the movement of the robot, which is something, again, that we need the environment to be able to talk about. So with the combination with this hybrid model, we can carry out proof. This proof is done basically by a tool called Isabel UTP that James is going to demonstrate. The proofs can be done in a compositional way, dealing with the modules and the documents separately, dealing with the differential algebraic equations as well. We have support in Isabel to deal with the differential algebraic equations, and using model checking. Model checking is a technique of theorem proving that is more automated, because ideally what we want, you see all these mathematical models are being generated automatically. The roboticists, they don't need to see it. What we want is for the roboticists not to need to do anything for the proof. We want them to push a button and get there. So for verification, we have that model that I mentioned to you, a model of the module and a model of the Robo World document. We can automatically generate or working to automatically generate sci-fi circus that will be read, that is read and accepted by Isabel UTP. But we also want to know, to prove a particular property, we can ally the use of the mathematical model of sci-fi circus in Isabel with the use of model checkers. These model checkers, they are more automatic, or can be more automatic than Isabel. And James is going to show to us how this thing works. We do realize that most people, as I said, do not know much about formal methods, but there are some people here that do, and I'm sure that all of you will be able to take something out of this demonstration. So, James, over to you, please.
Thank you, Anna. Stop sharing your screen so I can share. Okay. Thanks. Yeah. I'd like to add my thanks to the organisers for giving us the opportunity to do this. So as Anna mentioned, we use Isabel UTP to prove properties about the Robo World assumptions and their composition with the RoboChart module. So I'm going to pop out of this and show you a simple proof in Isabel. So this, you don't need to understand this proof, but it's a proof of a simple fact from group theory. And this is a proof that I've written myself, and it's very readable, but we, of course, don't want users to have to write proofs like this. So Isabel also contains a lot of automated proof facilities. So instead of writing out all of this proof, we can instead use this tool called Sledgehammer. Just press this button and it calls out to automated SMT solvers, which produce proofs that then can be fed back to Isabel. So here we can obtain a one-line proof, which is calling an internal tactic that Isabel uses. But I've got this more lengthy proof so I can show you some of the different features that Isabel has. So we can state assumptions of the fact that we're proving. So we have an account of what we're assuming going into a proof, and that is important from the perspective of Robo World, where we're stating assumptions on the environment. And then we have the fact that we're proving here, and we have all the regular mathematical notations. So we've got addition, inequality, and implication here. And the proof begins here, and we can obtain values from the assumptions. And we can also introduce assumptions coming from the left-hand side of an implication, since those are logically assumptions. And then we have an equational proof here, where we're just going down a chain of equalities. And each of these sub-facts within the proof can be proved via use of a tactic from among the tactics that Isabel provides. So we have this blast tactic, which implements a Tableau prover that works quite well when we're instantiating quantifiers. And this invokes Isabel's simplifier, which applies a number of simplification rules, and we can extend the set of simplification rules it applies by, so here we're including different facts from among the facts we have, and we can name the different facts as we're going along so they can be referred to. And then finally, we have the fact that we're showing at the end here, and we're just applying the calculation we've done above and applying, using it as the simplifier. And then the proof ends here. So Isabel has a lot of different proof tools that can be used, so it can give quite powerful and flexible proofs, but it also has some automation, and I've only shown part of what Isabel can do here. But we also have Isabel UTP, which is an implementation of unifying theories of programming, the basis for Sci-Fi Circus, on top of Isabel. And that gives us the tools we need to define Robo World models within Isabel. So we can recreate this semantics that Anna showed earlier, because we have parallel composition, so we can maintain this structure of the RoboChart module and the mapping process and the environment assumptions. And we have channels for communication, so we can have the mapping information events and the service events to communicate between the individual processes. And we have an implementation of differential equations in Isabel UTP, so we can represent the robot movement. And so Isabel provides a lot of power for proof, but although it does provide some automation, as I showed, we can get more automation, but less power to state the facts we want to prove using model checkers. And we're using two main model checkers for this work. We've got RoboStar, which is a hybrid model checker, and FDR, which is operating on a discretized version of the model. I'm going to mainly focus on RoboStar here, as I want to show you the hybrid model checking facilities we have for Robo World. So we start by building a model of the Robo World document that corresponds to this, but it has to be specialized to the facilities that the model checker can support. So the model checker is effectively operating over states and transitions, and these transitions can interrupt the evolution in a state, so that is used to implement this interruption here. And a lot of model checkers don't support parallelism, so we're writing our models in a tool called SpaceX and using a tool called HIS to flatten the models so that we get an equivalent semantics, but it makes it accessible to a broader range of model checkers, and particularly the facilities of RoboStar, which provides the model checking facilities that we need for Robo World. And then I've got a short video showing a run of RoboStar for the Ranger model that Anna presented earlier. So this is running it in a terminal, and we're feeding the model to the RoboStar command here, and it produces an output where it's spending time in each of the states and then checking whether it has to transition out of a state. And at the end, it's generating a plotting file. And these plotting files can be used to produce graphs like this. So from this, you can see that the X position of the robot, which is plotted on this axis, evolves over time so that it goes towards the obstacle, and then when it gets within range of the obstacle, it stops, turns around, and then moves away from the obstacle in the opposite direction. We have other graphs. So we have the Y position, which is staying within quite close to its starting position of 3. There's a slight bit of drift because it's not pointing perfectly along the axis. And we have a plot of Y position and X position. The obstacle is in the middle here, so it's moving from here towards it, and then when it gets within range of the obstacle, it sees there's an obstacle and turns around and goes the other way. We've also got a plot of the orientation of the robot, where we can see that the robot does in fact turn around. It's not just stopping and then reversing. And so all these values can be checked by the model checker, and that helps us to determine how the variables evolve over time, which isn't always easy to construct proofs about if the differential equations are quite complex. And it also helps us to obtain bounds on the possible values of the variables, which can be passed back to proofs in Isabelle. And in addition to determining the values of the variables, the model checkers can also check properties of the model, such as whether a particular state is reached. And I've got a small example of that. So you don't need to understand the equations here, but effectively what this model is checking is whether a particular value crosses 0 within a certain amount of time. So if it does cross 0, then it goes to this crossed 0 state at the bottom. And if it reaches the time, then it goes to this timeout state in the corner here. And then RoboStar can be used to check that we don't reach the timeout state. And because this model is quite large, I can't show you it running in full, but I've got a screenshot of the result of running it here, where you can see it's spending time in the cross 0 state at the end, and then after it's generated the plotting file, then it performs some safety checking, and the result of the safety checking is that it's safe because it never hits the timeout state, which is marked as unsafe. And so we can use that to validate properties that we need of the model, which can also be passed back into an Isabelle proof. And so that's just a tour of some of the verification facilities that we use with Robo World. I'm going to pass back to Anna to conclude.
Thank you, James. I will just now say a few concluding words, that's all, and then we are finished. So basically, what is the take home? Can you see my screen? Yeah? So what's the take home message?
Yes.
The RoboStar framework is a framework for model-based software engineering for robotics. It has several domain-specific languages. Robo World is for these operational requirements. It has sub-languages that allows you to include diagrams from RoboSim to describe these requirements. But it's an important tool to tackle the reality gap because it's capturing the assumptions and has this mathematical background that allows us to carry out proof. In future, we are going to carry out more case studies. We're very keen to get more and more documents and evolve with the language. The language is by no means a mature language, but also to explore compositional verification. I think what we have shown is that it's possible to allow roboticists to write English and we get mathematics for them. Thank you very much. I'm happy to answer any questions.
Thank you very much, Professor Anna. That was fascinating, very good information. You really actually clarify how can we define operational requirements in robotics. You explained the modeling that you are using. You have shown the practicality. James actually, and also Gustavo, you have explained how practically these models can help. I would be pleased if there is any questions or maybe anything the audience want to say. We are here.
Perhaps
Yeah.
Tom asked the question earlier, so perhaps he can be given the opportunity to ask his question so he can clarify what his concerns are about the tank.
Okay.
And perhaps we can have a chat about that as well.
David, can you unmute Tom, please?
Yes, he's unmuted now. It doesn't. He's muted himself again. So.
Right. Okay.
Yeah, maybe.
Okay, I'll try and address his question. I don't understand why he's worried about when the tank is not 100% full. I was giving there an example of a simplified model where I only was worried about it being full and being empty, because those would be the points where there is a concern in the simplified model, right? So I think I defined an operation that would have the precondition of the operation that the tank was full, that the spray was going to work if the tank was full. And then we also defined when it would become empty. So we will, the real example needs to be more elaborate than that. This other serious question about reliability. I wonder if, I don't know what MTBF stands for, but I think he's concerned about as failure models or failure rates and so on. We haven't dealt with failure rates of the robot, and I expect that's something that I kind of brushed over. We have, as I said, a language, that P model language, a physical model. That's where we really give details of the physical components of a robot. We can say what are the rigid bodies and how they're connected by joints, and what are the sensors, what are the actuators. And our theory, our sci-fi circus and our UTP allows us to deal with probabilistic and uncertainty, probabilistic behavior and uncertainty. The vision that we have is that we have dealt with probability and the semantics of probability at the level of RoboChart, so that colleagues can use probabilistic algorithms. Probabilistic algorithms are very important for swarm robotics, which is a very an area of application which are very keen. So we handle the probabilities in that context. My vision is that we will use the P model to identify the issue of failures in the model, possibility of failures of the physical model. But that work has not been done yet, and that would be a natural way of including facilities for that in Robo World. Okay, and he asked me, where do we get P model info? James, can you get the link for the RoboSim physical model report that's in the RoboStar website, please, while I answer?
Yes, I'll do that.
And then he will put it in the chat, Tom. Thank you very much for your questions. There is another question here. I remember Ross a few years ago. What's the difference with this software? And to refresh my knowledge, check this. Okay. Right, I don't know that that website. What's the difference between ROS and what we're talking about? ROS is a middleware. ROS is an artifact for programming. So it's very interesting, and it's very good that it is becoming, on one side, it's very good that it's become widespread. One of the problems of the current situation is that there is no standardization between the various simulators. So there are loads of robotic simulators, reactive simulators out there. And if you write code for one, you want to use another one, you throw your code away and start again, because their libraries are completely different. Sometimes their languages are different as well. And so there is quite a problem in terms of this variety in the simulation world. And it is a problem because no simulator normally caters for everything you need to simulate, and people need to use various simulators. ROS makes this a bit better because ROS is its simulator, and people are starting to use ROS for simulation as well as a middleware for programming, but it's code, right? And it has lots of problems if you are dealing with safety critical systems. ROS is, for example, it's not a real-time operating system at all, right? And that's code. From my point of view, what we want is to write a RoboChart model. That's the workflow that our colleagues in robotics want. They want to write RoboChart models, generate the software model for the simulation automatically, then create a physical model of the robot, then create a physical model of scenarios, and then document their assumptions in the Robo World. And with that, we should be able to actually, just with the RoboChart model and the P model and the scenario model, we should be able to generate a simulation automatically. At the moment, our work is targeting two simulators, Gazebo and Copilha Sim. But we have a colleague that is also looking into ROS, so that we can generate automatically code that will use ROS. We should not, when we're thinking about the design of the system, when we want to think about the operational requirements, when we want to think about establishing the core properties of our system or providing evidence of the quality of our system, we should not be having a code-centered view. That is really something I'm passionate about, that RoboStar team is passionate about. We don't start coding, we start writing models like every engineer. Okay?
Thank you very much. Thank you. Any more questions or comments, maybe?
There are more messages here. James has put a couple of links for the report about P models.
Yeah, also, actually, I put your Google Scholar link. Also, I put your the Centro website and your profile at University of York. So if you need more information, please use these links.
Mm-hmm. And I'll put yet another one here. That's part of what James has put there. But if you want to know more about RoboStar, you can look in this website there, and that talks about the work of RoboStar York, RoboStar Norway, RoboStar China, Brazil, France. That is the website of the Center of Excellence.
All right. Okay. Thank you very much.
Thank you,
Professor Anne. Thank you, James. Thank you, Gustavo. Thank you, everyone who attended or who's watching this webinar. It was very useful, and hopefully we may get another webinar in the future with more development in this area, in the RoboStar or the software engineering for robotics. Anything, Professor Anne, before we finish, you may want to say?
Thank you very much for the invitation again, and thank you for the opportunity. It was really interesting to talk to your community. People are asking how to download the software. If you go to the RoboStar website, we will find the Robo tool there and a lot of documentation. If you have any difficulties, just send me an email. I will put you in touch with people who can help. Thank you so much.
Yeah, James, anything to say before we finish? James?
Not particularly, no. I just thank everyone for watching, and yeah, thanks for inviting us to give this talk.
Thank you, James. Gustavo?
Thank you very much again. It has been a pleasure to be here talking about Robo World.
All right. Okay. Thank you very much. And thank you to everyone who participated. Thank you.
Thank you. Bye-bye.